Okay, YouTube, in my last couple of videos, we talked about combinations of functions. That is, if we had two functions, f and g, what we would get as a new function if we added, subtracted, multiply, or divide them. In this function, we're going to talk about the composition of two functions, or what we get when we compose two functions. So basically, you can think of this as putting a function into a function. We are very used to, if we had, say some function f of x equal to x squared, plugging in actual numerical values for this. So for instance, you would just do this, and you'd say, well, I'm plugging in 1, and I get an output 1. What we're attempting to do in this video is essentially saying, well, what if I had some function g of x, and I say, let's go put g of x into f of x. We would get some new function that we call f of g of x. As a matter of fact, you see I have this written here where g of x is the input and not a numerical value. So the first note I want to make here is essentially this. In terms of notation, we can write f of g of x thusly, and we say f of g of x where this little o stands for the of part. Okay, so we have fog x, and I just want to point some things out here. We could actually plug f of x into g of x. We'd have goff, it would look like this here, and that would just be really this, what we get when we plug a function f of x into g of x. And while, we're on this note, one more, we say we could even do like foff or gog of x. We could plug a function into itself. The idea being that you can plug functions into other functions and get what we call a composite function, or a function composed of two functions. So really quickly here, I want to talk about domain. As a matter of fact, we're going to come back to this, however. I've got a nice little trick for you to be able to find the domain of compositions, but I do want to say this. The domain of the composition here is really the set of all x in the domain of g, such that g of x is in the domain of f. So in other words, what we're saying here is we have some initial relation, g of x, that we're plugging into f of x. But initially we had g of x had all of these x values in its domain, and when we plug them in, we get some outputs, or g of x values. We're now taking the outputs of g of x and we're plugging them into f of x, and we get some new f of g of x. So really this composition just takes us straight from x over to f of g of x. But what we're saying about the domain is it's all x values that were in the initial relationship, such that also the outputs for that right there are in the domain of f of x. Like I said, I will explain that at the end of this video when we find the domain of this composition over here. But let's do this. Let us go ahead and discuss this composition that we see here. So we have some f of x equals x squared minus 9. This is just our quadratic parent function, some parabola that's been shifted down 9. And then we have g of x, which is this square root function here, which we'll want to take a look at its graph in order to talk about it. But what I want to do right now is essentially find f of g of x. So recalling that f of g of x, we would write it f of g of x thusly. We could also say that it's f of g of x. What we're really doing is, first of all, identifying that we're plugging something into f of x. So when we plug something into f of x, that means everywhere I see an x up here, we're going to go ahead and take it out, and we're actually going to plug in its input. Now, g of x is the input in this case. So we'll do some substitutions here. We have a g of x squared minus 9, where g of x is the, let's switch colors here, the square root of 9 minus x squared. So we know what happens when we square a square root. We actually get a natural radicand here, which is just 9 minus x squared minus 9. And I notice that these cancel out, and I just get negative x squared. And I want to actually highlight this here. This is f of g of x. So this is how you would run a composition, and I would encourage you to go back and try g of f of x and then show that it's not always the same thing, okay? So as far as finding the domain of f of g of x is concerned, this is kind of like two domain problems in one, I've heard it said. So basically, we can look at it this way. What I want everybody to do is this. I'll write this in. Find the, let's see if I can get it to type, text. There we go. So step one is always going to be this. Find the domain of the inner function first. Do not do this. Always do this. What we'll do next is this. Find the domain of the new composite function. And then what we'll do is this. The domain is the overlap of these two domains. Okay? So looking at both of these functions up here, my initial instruction was essentially this. We are going to find the domain of the inner function. And when we talk about the inner function here, I notice that the inner function in this case is g of x. So we say, well, what is the domain of g of x here, okay? And I notice that the domain of g of x is actually very restricted. We can't have negative values in here. So I could say one way to do this algebraically is to say, well, what we need to do is make this greater than or equal to 0. It can't be negative, okay? And then solve for this. But I think one really easy way to do this is actually just go look at the graph of the relationship here. So, oops, went to the wrong spot. We want to go to Desmos. And what we'll do is we'll type in this function here, f of x equals, and we had x squared minus 9 is our f of x. We can see here that if I scroll out, this is just our parent function f of x that's been shifted down 9, and it goes up 1, right 1, and then we have this parabola. If we look at the square root function, well, g of x equals, and we had sqrt, square root of, and it's 9 minus x squared. The interesting thing about this function is we notice that its domain, it looks like, is negative 3 to 3, and it includes negative 3 and 3. Basically, anything that is larger than positive 3 or less than negative 3, think about what's going to happen when you plug that in here. When you square, say, 4, you would get 9 minus 16, which gives you a negative 7, and we can't take an even index radical of a negative number. That's an imaginary result. So just by observation, let's go back and write in what the domains of these functions are. I notice that the domain of this one here is just negative infinity to infinity. That's the domain of this one. Okay, but the domain of the inner function we just noticed was negative 3 to 3 on that interval, and it's inclusive, so we're going to include negative 3 and 3. So as far as find the domain of f of g of x, here were the two things that I told you to do. First of all, find the domain of the inner function. So the domain of g of x is this negative 3 to 3 inclusive. Now, find the domain of the new composite function. Now, one would say negative x squared actually has a domain of all real numbers because it's a parabola. It's a parabola that opens downward. As a matter of fact, let's just go graph this. We say, what would f of x, let's do h of x here, h of x equal to negative x squared look like? You notice that we just have our quadratic parent function that's been reflected over the x-axis. But I want you to notice it looks like its domain is all real numbers. That's what it looks like. But don't be fooled. This actually, the domain, we're going to write this as domain not negative infinity to infinity. And the reason why I can say this is because what it's going to be is the overlap of the two domains. So what we've done is this. We found the domain of the inner function. Check. We found the domain of the composite function, which appears to be negative infinity to infinity. Okay, check. My question is, where would these two intervals overlap? So considering the entire x number line here, we say one function is defined all the way across the number line. That is the composite function. And then the inner function, how about we switch colors here? We'll go with like a green. The inner function was only defined between negative 3 and 3. So if we said, well, where does the composite function exist? It only exists for the overlap of these two functions right here. So again, we found the domain of the inner function. We find the domain of the composite function. And we say, where do these two things overlap? So we could say the domain of this function is just negative 3 to 3, and it includes those because we can just see that visually here where they overlap. Cheers.